In Chapter 5, we're going to be looking at trig identities. So these are equations that are part of the identity of the trig functions, and we're going to use them, throughout this chapter to solve problems, but we have to verify them, and so that's what section 5.1 is. We're going to verify some equations that are true, and we're going to start off with just listing the identities. The reciprocal identities, reciprocal is a fraction that's been inverted, and so these are our definitions of sine, cosine, and tangent, and then cosecant, secant, and cotangent as 1 over another trig function. These should look very familiar from our chapter 4 work, Our quotient identities, tangent of theta is sine over cosine because on my unit circle, my y value at any point is sine, and my x value is cosine. My cotangent is just that same fraction but inverted. And the Pythagorean identities, the first one is the one that if you can't remember any of the others, the one you need to know is sine squared theta plus cosine squared theta equals 1. So if I have a right triangle, and this is theta, this side is cosine, and this side is sine, and I know that x squared plus y squared, or a squared plus b squared, equals r squared, or c squared, So we know a squared plus b squared equals c squared for a right triangle. Well, here a is cosine, and we write the square with the function, not with theta, because we're squaring the cosine value, not the angle, plus sine squared theta. And on the unit circle, my hypotenuse is 1, so 1 squared is 1. Our even and odd identities talk about the shapes of the graph. You may remember even and odd functions from Algebra 2, but if not, we're going to look first at our graph of cosine, So cosine at x equals 0 or theta equals 0 starts here and it goes like this, and then it's symmetric over here. So if I go the same value of theta this way and negative theta this way, I am going to have the exact same value of my function. So taking the cosine of negative theta doesn't do anything. I'm just taking the cosine of theta. And because secant is 1 over cosine, it follows the same rule. For sine of theta, my pattern looks like this. And I know it's not a smooth curve, but we remember this from the second half of chapter 4. And so if I go the same theta this way, I am all of a sudden now at the same value from the x-axis, but they're opposite. So the sine of negative theta equals negative sine of theta. So it's the same as taking a vertical reflection of that same original graph. Cosecant is 1 over sine, so it has the same property. Tangent of theta, remember is centered at the origin, so it looks something like this. So if I go theta this way and theta this way, this one it's very clear to see that the values are not the same. So the tangent of negative theta equals negative tangent of theta. And cotangent is the same format because it is 1 over the tangent of theta, so again it has that same property. Now, you do have to memorize these for an identities quiz that will come up very quickly, but then after that we will give you the identities to use on tests and quizzes after that. So now we're going to verify some identities. This is what your homeworks are going to look like for the next few days, and this is going to be a large portion of what is on your quiz over 5.1 and 5.2. So when you are given these instructions, you always want to work with only one side of the equation, and you want to transform the more complicated or the more complex side of the equation into the simpler side. So you'll have one side that's your goal, So instead of hashtag relationship goals, you're going to have pre-cal goals, So in example 1, our goal is the secant of x, because that is a single thing and that is simpler than multiplying two things together. All right. In example 2, the cosecant of x is going to be our goal, that we want to make the other side look like that. So we have some varying strategies. Our first strategy is to change things that are not already in terms of sine and cosine into sine and cosine. We won't always do this, but this might be a good place to start. All right, so cosecant equals 1 over sine of x, and tangent of x equals sine of x over cosine of x. So when I combine those into 1 over the sine of x times sine of x over cosine of x, we can now see that sine of x cancels. And so we are left with the left side of this equation being 1 over cosine x, which is the same thing as secant x, which was our goal, so we're done. In example 2, we're going to do this a similar process, but now cosine of x doesn't have to change, sine of x doesn't have to change, but cotangent of x is going to be cosine of x over the sine of x. So what we have here is I have cosine x times cosine x all over sine x for that first term, and then plus sine of x. Well, I can't add these because I don't have common denominators. So what we're going to do is we're going to take this second one and multiply by sine x over sine x. So our new left side of the equation is cosine squared of x, all right, over sine x plus sine squared x over sine x, which I can combine cosine squared x plus sine squared x all over sine of x. And the top of that equals 1 based on our Pythagorean identity. So that is 1 over sine of x, which equals cosecant of x. That was our goal, so we are done. Sometimes when we want to verify an identity, we don't have any terms to change into sine and cosine because they're already there. So another strategy is to factor out a common factor from all the terms. Okay, our goal is still this side. All right, that's way less complicated than the left. May be the left sometimes is the simpler one, but in this case, it's still on the right. And so what I have in both the first term and the second term on the left is the sine of x. So I can factor that out. So I have the sine of x, and when I pull that out of the first term, sine of x divided by sine of x is 1. And then the sine of x times cosine squared, when I've divided out sine of x, I'm left with just cosine squared x. And then that equals sine cubed of x. The reason I've left the right-hand side in is we are now going to divide both sides by sine of x, which means that my new equation is just 1 minus cosine squared x equals sine squared x. I'm now going to point out something that you'll want to remember. So this equation here, when I take the Pythagorean identity where cosine of x and sine of x, all right, we have cosine squared x plus sine squared x equals 1. If I subtract cosine from both sides, then I have 1 minus cosine squared x equals sine squared x. All right, so if I see this equation, I'm automatically done. The other way I can do that is if I subtract sine squared from both sides from the original equation, and I get cosine squared x equals 1 minus sine squared x. So either way, if I saw any one of these three equations, they're all the same thing. So I can stop there, I'm done. Sometimes it's not going to be so obvious what our strategy is. here, I'm going to say that this looks a lot less complicated because addition is always less complicated than a fraction, right? So in this case, I'm going to want to separate a fraction because that's what's left on the left. So I have 1 over cosine, and then that is added to sine over cosine. All right. I could also have done this the other way and set this is what I was going to find, and then I know that secant of theta is 1 over cosine theta, and tangent is sine theta over cosine theta. So I have just written identical statements, and so I know that they are true. All right, but I'm going to go back the other way. So again, this could be secant of theta, and I know from my identities that this is tangent of theta, which is what I was looking for here. So I'm done. Or on example 5, 1 over cosine theta plus sine theta over cosine theta. I have common denominators, so I can combine them, which does indeed match the side I kept the same, and so either way I verified it. Okay. Personally, I think the separating the fractions might be a little bit easier, but if it's easier for you to turn the secant of theta and tangent of theta into sines and cosines and then combine, when it works out, that's a great way to start, but sometimes that won't get you down the path you need as quickly as the other way might. On example 6, the left side is just not very fun looking. So I have 2 fractions, not common denominators. In the first fraction, I have an expression that has addition in it, but the right-hand side is going to be our goal, because that is definitely the simpler side. So I'm going to work this 2 ways. The first time I do it, I'm going to work it the way that you technically should work it, all right? But then I'm going to show you a shortcut that may help you see the algebra a little bit better. So our hint, our other strategy is a common denominator. If I have 2 fractions, finding a common denominator will very often help. So the common denominator, all right, these 2 denominators currently have no factors in common. So I'm going to take the first one, sine of x over 1 plus cosine of x, and I'm going to multiply it by sine of x over sine of x. And then the second one, I'm going to multiply it by 1 plus cosine x divided by 1 plus cosine x. So now I will have common denominators once I simplify that. So the left-hand side, it's just sine squared x over, in this case, let's keep it like it is right now in the bottom, all right, and not distribute that. In the second one, however, I have something here, it's added, and I'm going to have to FOIL. So my first is 1, so it's 1 squared is 1, and then I have outer is 1 times cosine x, and then the inner is cosine x, so I have 2 cosine x, and then I have the last is plus cosine squared x, all over that same denominator, 1 plus cosine x times sine x. I now have 2 fractions with common denominators. I can add the whole thing. Okay, so the sine squared of x plus 1 plus 2 cosine x plus cosine squared x all over that 1 plus cosine x times sine of x. It may look like we can't combine anything, but if I see sine squared of x and cosine squared of x, I know that those 2 together equal 1. So I can substitute that in, and so my fraction becomes 1 plus 1 is 2, plus 2 cosine x, all over that same denominator. And now I actually have to scroll a little bit. And I can then factor out of the top. I know we just loved rational expressions in Algebra 2, but I can factor out a 2. So I have 2 and then times 1 plus cosine x. And now we see why we left the bottom the way it was. Because 1 plus cosine x is in both the top and bottom. So I just have 2 over sine of x. 2 over the sine of x equals 2 times 1 over the sine of x, which equals 2 times the cosecant of x, which if I scroll back up, that was indeed my goal, and so I am done. I'm going to work the same problem a second way, though. So we're going to start with the same identity we want to verify, sine of x over 1 plus cosine of x, plus 1 plus cosine of x over sine of x, equals 2 times the cosecant of x. So I know that this looks really ugly and it's a lot of letters and a lot of words. So I'm going to say sine of x is just, for any value of x, it's just some number. So I'm going to say sine of x, I'm going to set that equal to a. And I'm going to say the cosine of x equals b. If you define these variables, a and b, you then can use them. You can substitute them into your original identity. And so you know that 2 times cosecant of x is 2 times 1 over sine of x. So that is 2 times 1 over a, or 2 over a. So when we get to that, on the left-hand side, we'll know we're done. So let's substitute in a and b everywhere we see sine of x or cosine of x. So my left-hand side becomes a over 1 plus b. And then this becomes 1 plus b over a. And while this still isn't super great, we still have 2 fractions, not common denominators. Now I am multiplying my first fraction times a over a, and my second one, just 1 plus b over 1 plus b. I still have to FOIL in the second one. So 1 times 1 is 1, and then it's plus my inner is b, my outer is b, so I have 2b total, and then I have b times b for my last, so b squared, all over a and 1 plus b. And my first fraction is just a squared over a times 1 plus b. And again, here, I'm just going to combine the top, a squared plus 1 plus 2b plus b squared, all over a and 1 plus b. It's a little bit harder to see when you can use that Pythagorean identity when it's set up like this. So just remember that when I have these, this means that a squared plus b squared equals 1. So I have a squared and b squared. I am going to simplify that. So I now have 1 plus 2b all over a times 1 plus b. So that equals 2 plus 2b over the same denominator. And again, I can factor out a 2. 1 plus b all over a 1 plus b. Those cancel, and I am left with 2 over a, which does match this. However, I can't stop here. If I substituted in a and b, the one thing you have to do is go back and now into this one. 2 is still 2, but 2 over a was sine of x, and that equals 2 times 1 over sine of x, or 2 times cosecant of x, which was my original pre-cal goal. if you struggle to see some of the steps in the algebra or work with sine of x and cosine of x with the algebra, this may be a very helpful tool. Just don't forget to, number 1, define your new variables, and number 2, to change back to sines and cosines in your final answer before you say you're done. In example 7, neither side of our equation looks simple. I have a fraction in both. But when the denominator is a single term and doesn't have addition, all right, like the first one does on the left, I would say that the right-hand side is your goal. All right, so remember, this is our hashtag pre-cal goals. So our hint here, so this is our another new strategy, is to multiply the numerator and denominator by the same factor. Well, let's see. I don't think multiplying by cosine of x over cosine of x is going to help. All right, so we're going to see if I can multiply this whole thing by 1 minus sine x over 1 minus sine x. This is not necessarily one you're going to be able to figure out on your own the first few times. It's okay. But hopefully you'll recognize from previous algebra classes that there's now going to be a difference of squares, all right, that is produced here. So our top of our fractions, we have to distribute, so I get cosine x times 1 minus sine x, which we will actually leave there for now, okay, because I'm going to see here in a second that when I FOIL the bottom, I get 1 plus sine of x minus sine of x minus sine squared of x. So we're going to leave the top alone. Bear with me. I'm going to come down here, and the top is the same. The bottom, though, plus sine x and minus sine x cancel. So I am left with 1 minus sine squared x, which, if you remember, I can use the Pythagorean identity, and this equals cosine squared x. So I'm going to plug that in. I have cosine x, 1 minus sine x, all over cosine x times cosine x. In which case, that cancels, and I am left with 1 minus sine of x in the top and cosine x in the bottom, which does indeed match my pre-cal goal, so I am done verifying this identity. We're going to use our same difference of squares approach when I have two different denominators here. Even though it's two fractions on the left-hand side, we're going to try the same approach, see if it works. And then our goal is to get that to equal 2 plus 2 times the tangent squared of x. Oh boy. All right. So I'm going to take this first one, I'm going to do this one separately. So I have 1 over 1 plus sine x times 1 minus sine x over 1 minus sine x. So I'm going to leave that top. I don't have to distribute anything because 1 distributed in is just what it is. So that is 1 minus sine x over, my first is 1, and then I have outer is minus sine x, inner is plus sine of x, and my last is minus sine squared x. Oh my goodness. But those cancel. And then 1 minus sine squared x is just cosine squared x. So this becomes 1 minus sine of x over cosine squared x. My second fraction, I'm going to do a similar process, 1 over 1 minus sine of x. But to get the same difference of squares effect, where my middle two terms cancel, I'm going to multiply by 1 plus sine of x over itself. So my top becomes 1 plus the sine of x, and the bottom is FOILed, 1 minus sine x plus sine x minus sine squared of x, which is 1 plus the sine of x all over. Again, these middle ones cancel, and 1 minus sine squared of x is cosine squared x. And because I now have two fractions that are added, and they have the same denominator, I can add these. 1 minus sine x plus 1 plus sine x all over cosine squared x. And in this case, negative sine of x and positive sine of x cancel, so I'm left with just 2 over cosine squared x. And from here, it's not really super obvious what the next step is. Usually, we've had something we could do, or a Pythagorean identity. Oh, well, in this case, we're not going to be able to use sine squared plus cosine squared equals 1, but I can use tangent squared x plus 1 equals secant squared of x. So we're going to use that. And we're going to look at the left side of our equation. So tangent squared x plus 1 equals secant squared x. I don't have anything I can do with that, but 2 plus 2 tangent squared x, I can simplify. I can pull a 2 out of it, and I'm left with 1 plus tangent squared x, which all of a sudden I can substitute in secant squared x. So now this right-hand side of our equation becomes 2 times secant squared x. And if I go back to my left side, 2 over cosine squared x equals 2 times 1 over cosine squared x. And since cosine is 1 over secant and secant is 1 over cosine, that is the same as 2 times the secant squared of x, which they equal, so I am done. In summary, these are just some of our strategies for verifying trig identities. You can always work in slightly different ways, and you'll still get there, it just might take a little longer. So, always work with only one side of the equation at a time. You may get stuck, like we did in that last one, and have to manipulate the other side, but try to stick with just one side of the equation, otherwise you're going to completely confuse yourself. Alright, you always want to try to transform the more complicated or complex side to match the simpler side. You're going to potentially look to express trig functions in terms of sine and cosine. And you're going to look for opportunities to use the basic identities. So those are the reciprocal, the quotient, and the Pythagorean are the three big ones. All right, if you have fractions or things that have factors you can factor out, try to factor things out. Try to separate or combine fractions, or if you have a square binomial, that's that whole difference of squares that you end up with. All right, look for opportunities to make things go away or to combine. And the bottom line is, if you don't see the strategy to use, just pick one, try it, and then just don't be afraid to stop and start over again if you're not getting anywhere. Don't necessarily erase what you have. Put a single line through it if it makes you happy. But you can start over, start from scratch, try a new strategy, and maybe somewhere in there you'll figure out the right path. It's okay. This is a little bit like figuring out a puzzle. Okay, so don't be afraid to stop and start over again. All right, getting stuck is part of the process on these. Okay, so I want you to not give up. All right. Remember, hashtag pre-cal goals.